Hi everyone, today's topic is type checking. Before diving into the details of type checking, let's look at this beautiful picture of our school. It's fall, right? And fall foliage is so beautiful. This picture was taken by one of my colleagues and he was so happy to see these beautiful trees. Now back to types, type checking. We are gonna have this language called TFAE today. TFAE is FAE with types. So this usual FAE syntax has one change, the red bit, type annotation on identifier. As we discussed last week, number related things are just num type and identifier is being used by named and they are introduced by one language construct function expression. When we introduce a name, now we need to introduce its type as well. Then what is a type? In this small language, TFAE, as you know, there are only two kinds of values, num v and closure v. What's the type of num v? Num type. What's the type of closure v? It's a function, right? So it's going to be an arrow type from parameter type to return type. In your final exam or in your quiz or whatever, we may ask you to extend the language with more features like multiple parameters and multiple arguments. Then you may need to extend this to multiple thingies, multiple parameters. And this TFAE, it's just simple extension of FAE with types. So its implementation in Scala has also very tiny change, meaning that this function expression has a usual parameter and body expression, but in addition to them, it has a type annotation for the parameter. Then what are types again? It's a new user-defined type, and type has two variants, number or function. Num_t for num_v's, number values, arrow_t for closure v, function values. Arrow_t has only two fields, parameter type and result type. So far so good, yeah? And because we are interested in types of names in the environment, in the type environment, we need to keep these kinds of information, meaning that typeinf is a map from names of identifiers to their types, right? So what do we do with type checking? When do we call them and what's the role of that? 타입 체킹이 무엇에 쓰는 물건인고? 그죠? 이거 뭐 하는 거예요? When we evaluate an expression, previously we just interpreted it. When we want to evaluate an expression, we just wanted to interpret that expression under an empty environment. Under empty environment, interpret this expression, and that was the value. But now what we want to do is to check its type before running, right? Check its type before interpreting it. So while checking the type of this expression, if it has ill type thingy, if it has ill type, 타입이 말이 안 되는 이상한 애가 있어요? While we are type checking this expression, if there's something wrong, we are gonna throw an error and we are not gonna interpret it. When we type check this expression under empty environment, when we type check the same expression under this empty environment, and if it type checking succeeds and we have a type of this expression, then we can run it. Then we can interpret it. If there is no such type, there was an error, so it's going to be no type, then we are not going to interpret it. What's the point of interpreting wrong expression? 타입 체커가 이거 타입 이상해. 그러면은 인터프리트 안 할 거예요. 나쁜 애를 못하러 인터프리트 돌다가 에러 날 텐데, 그죠? 에러가 안 날 수도 있으나 나쁜 애잖아. 인터프리트 안 할 거예요. If there's a type error, we are not going to interpret it. That's the point. Another good thing, cool thing is that when we check the type of an expression and we have some type, well type, right? Then the secret is when we interpret that expression and gets a value, the value's type is this tau. We're going to learn that later. So there is an analogy, there is a similarity between runtime interpretation and compile time type checking. Type check takes an expression and a type environment and produces a type. When we type check an expression under this type environment, gamma, it either produces a type of this expression or throw an error, right? When we interpret an expression under an environment, when we interpret an expression under some environment, we're gonna have a value. So for those expressions, environment maps names to values. If we have some identifiers in this expression, this sigma keeps the information of values of those names. So while we interpret this expression, if we encounter some names like that, right? Or what? Flower. That's the name of some identifier. Then we'd like to know their values. We need to look up this environment. If there are no values of them, it's going to be free identifier error. While we are type checking this expression, we may have those identifiers. Then we are going to check their types in this gamma. If there are no types for them, it's going to be type error. Meaning that those XY flower, they are introduced by some function expression, right? Identifier.e. And in that function expression, those names should be with their types. Okay, then let's type check that expression. Type check again one more time. Takes an expression in a type environment, produces a type. Type check takes an expression and a type environment and produces a type. Depending on the expression, right? We are gonna pattern match this expression. What's gonna be the first expression? Yeah, you know that. The simplest one, number. Whatever the number it is, we do not really care about the actual value because it's type checking. Type checking is not interpreting. Type checking is not evaluating. Type checking is not runtime. We do not care about the actual values. We just care about its abstract value number, right? So whatever the value is, whatever the actual value number is, under any type environment, number has the type num. So what's going to be this one? The type had two variants, right? Num t and arrow t with primary type and return type. So what is it going to be? Yeah, that's simple, right? Num t. So we have this typing rule saying under whatever environment, under whatever type environment, when we type check an expression, which is number, then the type is going to be num. The type is going to be num t. That's going to be our implementation of typing rules. The next one, addition, right? What was a rule for the addition? Under whatever type environment, the type of E1 plus E2 is, in order to know its type, we need to know the type of E1 and E2. Let's check that. Under the same type environment, the type of E1 should be numpty. Under the same type environment, the type of E2 should be numpty. If the types of E1 and E2 are both numpty and numpty, oh, very good. Then the type of the whole thing is gonna be numpty. Let's implement that in Scala. How? Let's see. Addition of L and R. We are going to type check the first sub-expression. We are going to type check the second sub-expression under the same given type environment. And they should be what? Numpty, numpty. They should be numpty. They should be numpty. The type of E1, the type of E2 must be the same with numpty. Then what? If both are satisfied, the type of the whole thing is not going to be numpty, right? And the actual checking of types, not the expressions, but the types are handled by this auxiliary helper function called must same, right? What's the type of must same? It takes two arguments and produces something. It takes a type and another type. How did you know it's type? Because type check function takes two arguments, expression and a type environment, and produces type. So the type of the whole function call is going to be type. So must same takes type and produces what? Haha, look at that. Must same takes type and type. Must same takes two types and produces a type. It just returns the same type. Okay, so it checks, hey, those two argument types, are you the same? So this is another helper function, same. If they are same, then return one of them. Because they are the same, it doesn't matter whether left or right is returned. Otherwise, throw an error saying the first type is not equal to the second type. Okay? Then what's the function? Same doing. Again, it takes two types. And produces a boolean. How did you know that? That's why it could be used inside this conditional expression part, right? And we are gonna match two types because in this simple TFAE language, there are two kinds of types, numpty and ROT. So if they are both numpties, they are true. If they are both ROT, then they should have primary types and return types. And those arrow types are the same only if and only two primary types and return types are the same. So those arrow types are the same when primary types are the same and return types are the same. Otherwise meaning the first one is numpty and the other is ROT, or the first one is ROT and the other is numpty, or the first one is ROT with some primary and return type, and the second one is ROT type with different primary type and return type, then false. Okay? Not that difficult. Finally, this no type function takes some message and then throw an error. No type. And the reason was this kind of message. These are our helper functions. No type throws an exception with using the given error message. Same function takes two types and produces a boolean saying whether those two argument types are the same or not. Must same function takes two types and if they are the same, return the same type. Otherwise, throw an exception. Using these helper functions, let's type check the remaining expressions. Identifier. How do we type check an identifier? Under a type environment, when we type check an expression, what do we do? Remember, under a given environment, how do we know the value of an identifier, we had to look up this environment, right? And see whether this environment has a value of this identifier. So we need to look up this type environment, asking, hey, you, do you have the type of this name? So we need to check whether this gamma has an information about this given name. So whether X is in the domain of the gamma. If it has not, then give it to me. Hey, gamma, what's the type of this name? That's the rule, right? How do we implement that? Type check an expression under a given type environment, and the expression was happened to be a name. What do we do? Ask the type environment, hey, do you have the type of this name? Then give it to me, or it's an error. So, hey, type environment, do you have the type of this name? Then give it to me. Otherwise, throw an exception saying, what? That name is a free identifier. Why? Because it was a bound identifier. Like there is some function call, a function expression like this. Then if it's bound, that should have type tau, and that mapping should be in this type environment. But we didn't have any type of this name, meaning it's a free identifier, meaning there's no function expression that introduces this name. Right? So far so good. Then function expression. Let's type check this function expression. Look at that one more time. Under type environment, when we type check this function expression, what's going to be a type, right? Function expression now has a parameter type, and in addition to that, it's type information and body expression. So it's a function expression, so we know it's an arrow type, and we know that the parameter type is given here, so we're going to use it. Then what's going to be the return type? The return type should be the type of the body expression. What's the type of this body expression? We need to type check that using this given environment, and we need to extend that to say this parameter type has this information. So we extended this type environment with the type of the parameter, and then check the type of the body. And if it's tau2, then the type of the function expression is tau1 to tau2. No news here, right? Nothing surprising. Let's implement that. Hey, what's the type of this function expression with parameter name, type information of the name and the body expression? We are gonna type check the body expression under which environment? This environment. Extend this type environment with this information. Parameter has this type information. Okay, so type check the body expression under this extended environment. This extended environment. Given type environment gamma is extended with this new piece of information saying parameter has type T. Yeah. And then what? The type of the whole thing. The type of this body expression is the type of the return type. Then the type of the function expression is what? Arrow type. Arrow type? Yeah, arrow T. Arrow T takes how many fields? 2. Parameter type and return type. What's the return type? The type of the body expression that we just made. What's the parameter type? The given parameter type. So, one more time. What's the type of the function expression? What's the type of function with the parameter name x, with the type of the parameter t and the body expression b? That's gonna be arrow t from the parameters type t, the parameters type t, right, to the type of the body expression, the type of the body expression, which was checked under this extended type environment, right? So far so good. So that's gonna be the first part. And we check the type of TFAE, which has number, addition and subtraction. We didn't see the typing of minus subtraction, but that's similar to addition. You should know that by now. And we talked about how to type check identifier. How did we do that? Check whether X is in the domain of gamma and get the type of X in the environment. And how about the function expression? This is it, right? That was that. Then what's left? E1, E2, function call. After the first break, we are going to talk about this checking, the type checking of functional call, and then move on. This lecture has only 2 videos, so let's take the break now and come back for the second part.